Welcome to physics class. In today we shall be running analysis on a mass that is resting on an inclined plane. The goal here is to discover and bring out all the forces that are acting on this mass and to be able to derive some important useful equation for this particular situation. So to understand the forces that are acting on the mass on an inclined plane, we need to pretend that this plane is not hooked up at an angle. Let's just pretend that the plane is still lying on the floor horizontally. So let's start from there. So this is the plane with the mass and is lying on the floor. Now, what are the forces that are acting on this mass? Good, you have an idea. The first force is the weight, and this guy is acting downward. The weight, and the weight is given as the mass multiplied by gravity is acting downward. Now, as this force is acting downward, according to Newton's law of motion, actions and reactions has to be equal, but they are opposite in direction. So as the weight is exercising an action to keep the mass going down, there is a reaction that is equal but opposite to the weight that is acting upward. So that is it. So that's the two forces that we can see, the reaction acting upward and against the weight acting downward. Let's say we decide to push this mass forward with a force. If we push this mass forward with a force, F. Now, for us to successfully push this mass forward, we must overcome an opposite reaction force known as the frictional force that is going to try to prevent us from moving this mass forward. It's just like rubbing your palm against each other. You can agree with me that when you place your two palms together and you decide to move one against the other, there is kind of a resistance that you notice in the course of doing that. And that is as a result of an opposite force that is trying to prevent you from doing that. And that is what we call frictional force. So if this guy is going to move this way, there exists a frictional force that is acting this way. So basically, that is the four forces that are acting on this mass. Now, as it stands now, everything makes sense because from the look of things here, we can see that the reaction force is equal to the weight, and the frictional force is equal to the force that is going to move the object this way. And according to the law of solid friction, the frictional force is directly proportional to the normal reaction force. And when we expand on that, we discover that the constant of proportionality is known as the coefficient of friction, which is dependent on the material and the surface that is involved. So this guy is the determinant factor that tells us who is who in the situation. So this becomes our first equation for this process. Now, but if we decide to lift this plank that is on the floor with the mass a little bit upward, the equation is going to take a new form, and that is what we want to achieve right now. So imagine if I decide to lift it up, something is going to happen. So if I lift it up a little bit, let's say I lift it up a little bit at an angle theta, you agree with me that this mass, every other force kind of is going to remain the same, but something is going to happen. Now, according to this, the forces that are acting on this mass that was lifted up a little bit include, we already have the normal reaction that is always acting perpendicular to the mass. Then the weight that is where the problem is going to start. The weight always acts vertically downward. That's always keep that in mind. The weight of an object always acts vertically downward, regardless of how the mass is hanging. So whether the mass is hanging at an angle or not, the weight is going to act vertically downward. Keep that in mind. So if the weight is acting vertically downward, if you notice that the reaction force has shifted, because it makes it a little bit difficult for us to quickly find the reaction force. When it was lying flat on the floor, it was easy for us to pinpoint that the reaction is simply the weight, which is mass times gravity. But unfortunately, in this situation here, there is a problem, and we need to find what the problem is. This angle at which the inclined plane is bent is going to affect how much wide gap this reaction force is going to be. Now, look at it this way. Now, where is this way supposed to be? It was supposed to be here, that's vertically opposite to the reaction force. So this is where the weight is supposed to be, assuming that this material is lying flat on the floor, but it is not, which means it's lifted up at an angle, and that angle, the wider the angle becomes, the wider the gap between the weight and the supposed position, the line of action of the weight. Now, this line of action of the weight is called the weight component, which this angle theta here is equal to this angle, because the wider, the more angle that is swept as you lift this guy up, the wider the distance between the weight and the supposed original position of the weight. So for this particular shape here that has even more wider coverage, we're going to see it clearer. So let's look at it here. You see, this is the weight. Now, this is the normal reaction. Now you can see that the normal reaction is only equal to this component of the weight, which is dependent on the angle theta, which is the angle that is formed as you continue to lift this up. The higher this plane goes, the wider the angle between these two guys. And then to get the reaction, which is equal but opposite to this, we simply express it in a component. So the component of this, because the angle is formed there, the component of this is going to be W cos theta. So that is the new thing that appears once an object is placed at an angle. Now, another interesting thing you need to know is that the higher you take this, it will get to a point where this guy will kind of try to overcome the frictional force and will try to slide down. And what is making it slide down is still the weight, but a different component of the weight. So you can see that this particular mass here has the weight being controlling its direction of movement. So for this particular mass to slide down here depends on the weight. For this mass to remain on this plane without sliding down still depends on the weight. It depends on the component of the weight that you are dealing with at the moment. So the component of the weight that is going to keep this mass firmly attached on the plane is this component, W cos theta. Whereas the component of the weight that is going to cause the mass to slide down freely is W sine theta. And these two components are very, very important as long as the case of forces that are acting on an inclined plane is concerned. And this component of the weight, for it to succeed in pushing this mass down this plane, it has to overcome a frictional force, assuming that this particular surface here is rough. But if this surface is smooth, it is going to slide down and with a high acceleration. But then if there exists a frictional force, then the frictional force is going to stop it for a while before it eventually slides down. And that is the frictional force there. It's acting in opposite direction to this. So if we pull this up together, we can see something really amazing. We can see that the normal reaction force is taking a new shape. It is now, according to on the inclined plane, is now giving us W cos theta. And if we expand on that, W is mg, we can see that normal reaction is giving us mg cos theta. Makes sense, right? Good. Now, if we decide to substitute what we have discovered here into this equation, which is the law of solid friction, we discover that the frictional force will now take a new shape, which is going to be the mu, which is the coefficient of friction multiplied by the normal reaction, which is now mg cos theta. And this is very important in the course of defining the frictional force. So similarly, we can also see that the frictional force, which we are looking at right there, is given, you can see, is equal to the weight force, that's the weight component that tends to push this mass down the hill. Okay, so if we pull that up, we can see that the frictional force can also be seen as the weight sine theta. And when we simplify that, we will see that the frictional force is mg sine theta. So this is the situation whereby the frictional force is equivalent to the weight that is going to push this mass to move downward. So now, with these two information about frictional force, if we pull that together, we may be able to ascertain what the coefficient of friction is. So let's quickly put that up. So if I wipe this part of the board, so if we combine this equation, so I'm going to call this one equation 1. So this becomes equation 2, and this becomes equation 3. So if I combine equation 2 and 3 together, we can see that mg sine theta, which is the frictional force, is equal to coefficient of friction mg cos theta. That's substituting f, and we just put the value of f into this equation here. So if I make mu subject formula, I will have to divide both sides by mg cos theta. So if I divide that by mg cos theta, so we can see something really amazing, and that is the coefficient of friction being equal to, we can see that it's not dependent on the mass because the mass cancels out, the gravity cancels out. It depends on the angle. The angle, we can see that sine theta all over cos theta. And from trigonometry, sine theta over cos theta is the same thing as tan theta. So if I put that up, we can see that the coefficient of friction is equal to tan theta. So you can see this. So these are the useful equation that we need as long as friction and the mass on an inclined plane is concerned.